Hello everyone, my name is Suji. Here I'm going to present our work on analyzing the impact of channel estimation errors on RIS aided systems and optimizing its data rate in the presence of these errors. This is an extended version of the talk that we gave at the conference ICC. So, a reconfigurable intelligence surface or RIS can be considered as a thin sheet that consists of a large number of reflecting elements. And these elements are capable of changing the electromagnetic properties of the incident signals, such as phase. And the interactions of these elements with the incoming signals can be controlled using a microcontroller. So we can configure an RIS to improve SNR, to enhance coverage, to increase data rate, and so on. For example, in this figure, we can see that an RIS plane extends coverage to a user to which the direct signal from its transmitter is blocked. So in this slide, we'll discuss configuring an RIS. For example, we have a single antenna transmitter and a single antenna receiver. The direct link between them is blocked by an obstacle. So the communication is through an RIS having n elements. Now consider its ith reflecting element. The cascaded channel through it, denoted by HI, is the product of channel gains from transmitter to the ith element and that from the ith element to the receiver. Then we can configure its reflection coefficient phi I in such a way to cancel the phase shift introduced by the corresponding cascaded channel. Then phi I becomes equal to e power minus j times angle of HI. Then the effective channel between the transmitter and receiver, denoted by G, which is equal to the sum of the product of cascaded channel gains and the corresponding reflection coefficients, becomes equal to sum of the absolute values of the cascaded channel gains. Now we can show that this particular configuration maximizes channel power gain of the effective channel gain. So from this discussion, it is clear that to configure RIS, we require accurate estimates of the cascaded channel gains. But in practice, these estimates come with channel estimation errors, which degrade the system's performance. And in the case of an RIS-aided system, these errors affect it in multiple ways, which we will discuss in the next slide. So for example, here we have a downlink TDD system. For it, the transmitter first estimates the cascaded channel gains from the uplink pilots. Then it uses these noisy estimates to configure the reflection coefficients. Then the effective channel gain becomes a function of the uplink channel estimation errors. After that, the transmitter sends data along with pilots in the downlink, and the receiver first estimates the effective channel and uses this estimate to coherently demodulate the data. Now, the channel estimate at the receiver captures the channel estimation errors both in the uplink and downlink channel estimations. So here our focus is on analyzing the impact of these estimation errors on the downlink data rate and optimizing it. So we consider the following system model. We have a single antenna TDD system. The direct link between the transmitter and receiver is blocked. So we assume the transmitter to RIS link to be a deterministic line of sight link. This arises when there are no scatterers around the transmitter and the RIS. For example, this happens when we place the transmitter and RIS at a height close to each other. Then the link between the RIS and receiver is assumed to be a Rayleigh faded ring for a rich isotropic scattering environment. Now we assume the following spatial correlation model, which depends on the inter-element spacing between the RIS elements. And this model is suitable for a Rayleigh faded channel. Then for this system, we consider the following two-phase training scheme. In the first uplink phase, the receiver sends n pilots. At that time, the RIS employs a DFT matrix based configuration. Then the transmitter estimates the cascade channel gains and configures the reflection coefficients. After that, the effective channel between the transmitter and receiver becomes a function of the uplink channel estimation errors. After configuring RIS, in the second phase, the transmitter sends a single pilot along with data to the receiver. Then the data signal at the receiver becomes a function of the downlink data power, the effective channel gain, the data symbol which is chosen from any constellation, and the additive Gaussian noise with variance sigma square. And the receiver first receiver first estimates the effective channel and uses this estimate to demodulate the data from the data signal. And we impose the following constraints on this system. The total energy the total energy spent during the uplink training is limited by a receive energy budget ERX. Similarly, the total energy spent during the downlink transmission is limited by an energy budget ETX, and ETX is divided between the downlink data and pilots using a parameter called the energy allocation factor alpha. So basically, alpha is the fraction of the transmit energy budget spent on the data transmission. So here our goal is to analyze the impact of channel estimation errors on the downlink rate and find the rate maximizing optimal alpha. So for that, first we need to formulate the achievable rate. So in the next few slides, I'll be discussing the major steps in formulating the data rate. Now consider the expression for the effective channel, and we can see that it's a nonlinear function of the noise epsilon I, where this noise enters through the cascaded channel estimates. Now, because of this complex form, its analysis becomes intractable. So we propose a tractable approximation for the effective channel, which is derived from the high SNR analysis during the uplink training. So here the figure plots the mean square error in this approximation normalized by the energy of the unapproximated channel gain as a function of the uplink SNR. And we can see as the SNR increases, the accuracy of the approximation improves, because of which the mean square error decreases. And even for a small SNR of 5 dB, we can see that the mean square error is close to 1%. It shows that the approximation is accurate even in the small SNR regime. So we use this approximation to understand the statistical properties of the effective channel. We derive its mean and variance in tractable forms, and we use these parameters to derive an MMSE estimator for the effective channel at the receiver, which we use to coherently demodulate the data. Furthermore, we prove that this effective channel is Gaussian when the number of elements is sufficiently large. And these results lead to the derivation of a tractable expression for the achievable rate. Here we will briefly discuss the proof for the Gaussianity of the effective channel. So we can write the effective channel as the summation of n correlated random variables, where this correlation is because of the spatial correlation among the cascaded channel gains. So here, having finite variance summons is not sufficient for central limit theorem to apply, as in the case of independent random variables. So we employ more sophisticated row mixing arguments for central limit theorem to apply, for which these 4 conditions need to be satisfied. Here, rho sup is the supremum of correlation coefficient as a function of a distance parameter n. We'll discuss more about this rho sup in the next slide. So here the first condition indicates the asymptotic independence of the summons. That is, as the distance between the corresponding elements increases, the correlation among the summons decreases to 0. The second condition states that the variance of the summons must be finite. And the third condition says that for infinitely large number of elements, the variance of the effective channel goes to infinity. Then the fourth condition says that the infinite sum of the correlation coefficients taken at sampled distances must be finite. And in our paper, we show that the effective channel satisfies all these 4 conditions. In this slide, we'll briefly discuss the function rho sup. It is defined as the supremum of absolute value of normalized correlation coefficients between the summand corresponding to the first element and the summands corresponding to all those elements that belong to a set Sn. So here Sn is the set of indices of elements whose distance from the first elements is greater than or equal to n d bar. Here n is an integer which is less than the total number of elements, and d bar is the height and width of RIS elements. So for example, here we have an RIS plane of 16 elements. Here S2 is a set of indices of all elements which are at a distance 2 d bar or greater from the first element. So which corresponds to all elements shown in pink. So one thing to note that for simplicity we assumed equal height and width of elements here, but we can extend this to the scenario when the height and width of elements are not equal. And for the setup that we considered, we can derive rho sup of n as shown here. Here beta is the variance of the cascaded channel gain, and here f is the Gauss hypergeometric function which takes the entry of the spatial correlation matrix R as input. Here I sup is the index of the element that solves this maximization problem. So here we present the Gaussian probability paper test for the real part of the effective channel. In these figures, we compare two functions. First function, which is shown in red, it is of the form x minus mu r by sigma r, which is a straight line. Here mu r is the mean and sigma r is the standard deviation of the real part. The second function shown in blue is of the form q inverse 1 minus CDF of real part. Here q is the Gaussian q function. Now we compare these two functions because we know that when the real part becomes Gaussian, the function q inverse 1 minus CDF becomes equal to the straight line x minus mu r by sigma r. We can see this in these figures. As the number of elements increases from 32 to 512, the blue curve becomes more and more linear and matches the red line over a wider range. And we have similar results for the imaginary part of the effective channel as well. And in this case, we can show that the real and imaginary parts are independent of each other, which verifies the Gaussianity of the effective channel when the number of elements are large enough. Moving on to the problem formulation. Here, following the steps discussed so far, we can formulate the rate as a function of a prelog factor, which is a fraction of data duration to the coherence interval, and a function called the SNR effective, which captures the cumulative impact of channel estimation errors. And we can see that it's a function of the transmit powers and unit energy random variable. Then our problem is to find the optimal alpha that maximizes the rate subject to the downlink data and pilot energy constraints. Here I present the optimal solution. We can show that the optimal alpha can be written as a function of two parameters, zeta and kappa, where zeta and kappa can be shown to be functions of system parameters such as transmit energy budget, receive energy budget, the number of RIS elements, etc. Here zeta is also a function of the coherence interval. Now substituting the optimal value of the energy allocation factor in the energy constraint, we can compute the optimal downlink data power and the optimal downlink pilot power. Here we benchmark the proposed scheme. The figure plots rate as a function of normalized receive energy budget for two values of normalized transmit energy budgets. Now, the blue curve represents the rate from Monte Carlo simulations, for which we do not make any approximation for the effective channel, and we compute its statistics from Monte Carlo simulations. We also find the optimal energy allocation factor numerically. Then the red curve represents the rate from the analysis. Here, the green curve represents the rate for the equal power allocation scheme or EPA. So in equal power allocation scheme, downlink data and pilots are transmitted with equal power. Then we can see that the proposed optimal scheme outperforms the equal power allocation scheme in terms of achievable rate. And furthermore, as we increase the receive energy budget, the gap between the rates from simulations and that from analysis decreases. This is because the accuracy of the effective channel gain improves. So here we discuss the impact of the energy allocation factor on the rate. The figure plots rate as a function of alpha for different values of coherence intervals. The solid line represents the rate from simulation, uh, in which we compute the rate for each given value of the energy allocation factor, and cross mark represents the optimum point of it. Then the circular marker is the rate at the optimal alpha from the analysis. So we can see as alpha increases, the rate also increases to an optimal value because we are spending more energy on the downlink data transmission. Then if we increase alpha further, the rate starts decreasing. This is because we are not spending enough energy on the downlink channel estimation, because of which the accuracy of the estimate decreases. So this brings out the trade-off in allocating energy for the downlink data and pilots. Coming to the conclusion, we analyze the impact of channel estimation errors on the downlink data rate of an RIS aided system. We saw that these errors affect not only the data demodulation but also the RIS phase shift configuration. And for this, we first derived an achievable rate expression for a two-phase training scheme that captured the impact of these errors. And for it, we first proposed a tractable approximation for the effective channel. We then proved that it is Gaussian when the number of RAS elements is sufficiently large, even in the presence of spatial correlation. We then derived the rate optimal downlink data and pilot powers. Uh, and we saw that the proposed scheme achieved a higher rate than the equal power allocation. Now, more details on this work can be found in our journal paper, which is shown at the bottom. And in it, we also considered the optimization of the pilot duration in the uplink and downlink. And we also extend our analysis to the case of cascaded channel grouping, which requires lesser number of pilots in the uplink. Then we also consider the channel model in which the transmitter RIS link is a non-line of sight relay faded link. With this, I conclude. Thank you for listening.